Welcome back to the Deep Dive. Today, we are strapping in for a journey into a technology that is fundamentally changing how machines, and by extension, you understand and process information.
Right.
We're going deep into the world of vector databases and vector search.
And our mission today is really to cut through the jargon.
Exactly. We want to show you why this technology, which allows computers to finally grasp meaning and intent, what the industry calls semantic understanding is, well, it's no longer experimental.
No, this is the critical inflection point for professionals, researchers, content creators, small law firms, or, solo consultants who deal with these vast, unmanageable mountains of unstructured data.
Text, images, proprietary reports, video archives, all of it.
All of it. For them, this shift is monumental. We are moving light years beyond rigid keyword matching to a system that understands the concept you're trying to express.
And for this, we've assembled sources that detail not only the core concepts and, frankly, the complex mechanics of vector DBs, but also the transformative, very specific scenarios for using them across specialized fields.
And we're really focusing today, I think, on the revolutionary impact this has on academic methodology, especially in the humanities and social sciences.
Yes, that and also the immediate practical wins for professional services. It's a dense dive, for sure, but we'll guide you through every nuance.
It's worth it.
Okay, let's unpack this, starting with the core fundamental problem that this technology solves. So, to really appreciate the solution, we have to first get our heads around the limitation we've all been living with for decades.
Right, the limitation of traditional computing. For most of the digital age, we've relied on what are called relational databases, or RDBs.
The classic spreadsheet model.
Exactly. Rows and columns. They are optimized for structured data, the things that fit neatly into spreadsheets, inventory logs, customer ID fields. And to be clear, they are superb for speed and accuracy when you're handling that kind of structured information.
No one's knocking them for what they do well.
Not at all. But the method they use for searching text, known as lexical search or simply keyword search, operates on a very strict, almost mechanical principle.
Which is an exact term or literal word match.
Precisely. We're talking about algorithms like BM25 or TF-IDF. They are ruthlessly efficient at looking for literal string occurrences. They calculate the relevance of a document based on, the frequency and the positioning of the exact words you provided.
So if I type in a word, it just counts how many times that word appears and where.
In a nutshell, yes. But the strength of that system, its precision, is also its fatal flaw when you're dealing with human communication.
Because human intent is just not that simple.
Not even close. It's inherently subtle, contextual, multidimensional, and this mismatch creates what we call the semantic gap.
And the semantic gap is this huge chasm between the rich complexity of human thought and the purely mechanical, very precise processing capability of the machine.
It's the perfect way to phrase it. The classic example that illustrates this failure perfectly is how concepts are related. If you search an archive for the word canine, a traditional system, relying on that string comparison, will almost certainly fail to retrieve documents containing the words dog, puppy, hound, or wolf.
Even though they all mean essentially the same thing in that context.
Exactly. They are semantically, conceptually, intrinsically linked. But the machine doesn't see that.
Why not?
Because the strings of characters are different. CANINE is not DOG. The machine is blind to the conceptual distance or closeness between those words.
Our sources highlight this limitation as the downgrade phenomenon, which I think is a great term for it.
It really is.
As the user, you have this rich, complex concept you want to explore. But because the machine is so literal, you are forced to limit that subtle idea, that rich intent, down to the machine's strict, precise keyword language.
You have to downgrade your thought process.
You have to guess what words the original author might have used and hope you get it right.
That's a powerful way to frame it. It's essentially a cognitive mismatch. The user has to adjust their intelligence and vocabulary to suit the machine's processing rather than the other way around.
Which is backwards.
Completely. Traditional search is fundamentally a filtering operation. It asks, which documents in this set contain the exact words X, Y, and Z?
Which means if I misspell a critical term or, like we said, use a synonym, my filter fails and I miss the vital information.
Absolutely. You get a false negative. And that's where the vector search revolution offers an entirely different proposition. It completely shifts the paradigm.
It's not filtering anymore.
No. Vector search is fundamentally an exploration operation. It asks, find me everything similar to the concept expressed in this query. That is the key difference that allows the machine to finally grasp human intention and context.
So if the problem is this semantic gap caused by keyword rigidity, then the solution has to be a technology that handles meaning directly.
It has to be.
So let's formally introduce the vector database. What is it really?
A vector database is a specialized, I'd say, next-generation database built specifically to store, manage, and index what are called vector embeddings.
Okay, we'll break that term down in a second.
We will. But the key thing to know is that it is the infrastructure designed from the ground up for unstructured data: text, images, audio, video. While a traditional RDB manages those rigid rows and columns, the vector DB is engineered to capture complex, multidimensional patterns and relationships.
The meaning.
The very meaning of that unstructured data. And today, its most critical job is serving as the core infrastructure supporting modern generative AI applications, especially something called Retrieval-Augmented Generation, or RG.
Which we will definitely get into later. But the magic, as you said, starts with the core mechanism. Vector embeddings or vectorization. How does a block of text or an image turn into a list of numbers?
So vectorization is the process where a sophisticated machine learning model, known as an embedding model, converts any unstructured input, a sentence, an entire document, a photograph, into a long list of floating point numbers.
It's a sequence of numbers.
A very long sequence, sometimes hundreds or thousands of numbers long. This list of numbers is the high-dimensional vector. You can think of it as the mathematical representation or a sort of numerical fingerprint of the content's essence.
And the underlying theoretical foundation for this is known as the distributional hypothesis.
Correct. And it's actually a pretty intuitive idea. The model learns that words appearing in similar contexts tend to have similar meanings. If you feed the model terabytes of human text, it starts to notice that cat and kitten frequently appear in similar grammatical structures and near similar descriptors like furry, small, or purring.
So it learns from context.
It learns entirely from context. As the model maps these words into this abstract, high-dimensional vector space, it places them at very close coordinates to each other.
This spatial relationship is one of the most intuitive ways to grasp the concept. If we take that classic analogy of vector arithmetic, which is really how LLMs handle analogy, it shows us that meaning has a kind of direction.
Precisely. The famous demonstration that really blew people's minds a few years ago is the relationship. Vector of king minus the vector of man plus the vector of woman equals
The vector of queen.
the vector of queen. The direction and distance in this vector space between king and man is semantically identical to the direction and distance between queen and woman.
That's incredible.
It is. It proves that the vector space successfully encodes these abstract concepts like gender relationships, royalty, and, critically, the relationships between them. It's meaning made calculable.
And that calculable meaning leads us directly to vector search. The fundamental principle is almost deceptively simple. Geometric distance equals semantic similarity.
That's the whole game. When you submit a natural language query, say, a complex question about a client case, that query is immediately vectorized by the same model. It becomes a single point in this vast vector space.
Your question is now a set of coordinates.
Exactly. The system then searches the database for the nearest neighbors, which are simply the vectors, the other documents or images that are closest to your query vector, because the vector for dog was placed close to the vector for canine during the learning phase.
The system successfully retrieves documents related to dogs, even if the word canine was never used in your query.
It's looking for the concept closest to your concept, not just the nearest sequence of letters.
So to quantify that proximity, that closeness, we use what are called distance metrics.
Yes, and we primarily rely on two major mathematical tools for this: cosine similarity and Euclidean distance.
Let's start with cosine similarity.
Cosine similarity measures the angle between two vectors. It's perfect for determining topical similarity. It focuses on the direction of the vector while ignoring the overall magnitude or length of the vector.
Okay, why is ignoring the magnitude important, especially for text analysis?
Well, imagine you're comparing a 5-paragraph summary of a corporate report to the full 80-page report itself.
Okay, they're about the same thing, but one is much, much longer.
Right. They discuss the exact same topic, but their vectors would have wildly different magnitudes or lengths just because one contains so much more text. If you used a pure distance measurement, the short document might seem completely irrelevant or far away from the long one.
Even though it's the perfect summary.
Exactly. Cosine similarity guarantees that because the two documents are pointing in the same thematic direction in the vector space, they are deemed highly similar, regardless of their length.
That makes perfect sense. It ensures you capture all relevant texts, no matter how verbose or concise they are. And the other one, Euclidean distance.
That's the one we all learned in high school geometry. It measures the straight line distance between the 2 points, like finding the shortest path on a map.
The as the crow flies distance.
Precisely. Closer straight line distance means higher similarity. While both are used, cosine similarity tends to dominate semantic search applications for text and meaning, while Euclidean distance is often favored in other contexts like image recognition or measuring differences in raw numerical properties.
This all sounds incredibly effective, but the reality of modern applications involves, well, massive scale. We're not talking about thousands of vectors. We're talking about systems that might manage billions.
Or even trillions.
Right. So if we are running a brute force comparison, calculating the exact distance from our query to every single vector in the database, we'd be waiting hours, if not days. How do we get millisecond search speeds at that enormous scale?
We rely on indexing, and specifically a set of algorithms called ANN, or approximate nearest neighbor.
Approximate, that's the key word.
That is the key word. Brute force comparison, which is called KNN, or exact nearest neighbor. It guarantees 100% accuracy, but it completely fails the test of practicality. The computational cost is just too high for any real-time application.
So the solution is the approximation. We have to accept a tiny bit of error to achieve massive gains in speed.
Exactly. ANN sacrifices a marginal amount of accuracy. We might aim for 99% recall instead of 100% in exchange for search speeds measured in milliseconds.
It's a trade-off.
It's a practical compromise. Think of it like a human quickly finding a sufficiently similar person in a crowd rather than comparing your target to all 8 billion people on the planet. This tiny compromise is what makes vector DDs the engine behind real-time services, like personalized recommendations, large-scale content moderation, and live chatbots.
So let's delve into the mechanics of the major ANN algorithms, because they really determine the performance trade-offs for different applications. We should start with the high-performance option, HNSW.
Right. HNSW stands for Hierarchical Navigable Small World. It's a graph-based algorithm, and it's highly favored for its speed and its accuracy. HNSW organizes all the vectors into a series of interconnected graphs, where each graph is a different layer of a hierarchy.
And this hierarchical structure is key. That's the core analogy of the expressways and the local roads, isn't it?
Yes, it's the perfect analogy. Think of it this way. The top layers of the graph act as these high-speed expressways. These layers are sparse, they contain fewer connections, but they span vast distances across the entire vector space.
So they let you jump around quickly.
Very quickly. When a query comes in, the search starts at the highest, fastest layer, quickly jumping across huge areas of the vector space to get into the right general neighborhood of the target.
So the expressway skips enormous amounts of irrelevant data right from the start.
Precisely. Once the search is close, it drops down to the lower, denser layers, which act as the local roads. Here, the connections are frequent and short, allowing for very precise, small-scale searching to find the exact nearest neighbors within that final neighborhood.
A high-speed start and a precise finish.
That's what gives HNSW its incredible performance metrics. But there is a major downside. The entire index structure often needs to reside in RAM for maximum speed, which drives up server costs considerably, especially at scale.
Okay, so that's a high-cost, high-performance option. Next, we move to IVF, the inverted file index. How does this clustering approach differ?
IVF uses a clustering algorithm, often something like k-means, to logically divide all the vectors into many distinct clusters, or buckets.
Like a massive mail sorting facility.
Perfect analogy. Before IVF, you'd have to search every single piece of mail in the building. With IVF, you pre-sort all the mail into neighborhoods, or zip codes.
And when a query arrives, how does the system use those clusters?
The incoming query vector is checked to determine which few clusters it is closest to, say, the 3 nearest clusters. The system then only searches the vectors within those 3 clusters.
So it drastically reduces the search space. Instead of billions, you're searching maybe a few million.
Exactly. And that immediately sounds much more memory efficient than HNSW because you aren't holding this entire highly connected graph in RAM.
It is. It's more memory efficient, and it's also faster to build the index in the first place. But here's the trade-off.
There's always a trade-off.
What happens to the vectors that sit right on the boundary line between 2 clusters?
Ah, right.
If your query lands near that boundary, the system might only check one cluster and completely miss checking a neighboring cluster that holds a vector that is technically closer.
So you have the potential for loss of accuracy for those boundary cases.
Right. And finally, there's LSH, or locality-sensitive hashing.
LSH is the pure speed for precision compromise. It uses specialized hashing techniques to map similar vectors into the same bucket. It's highly effective for dealing with extremely massive data sets, particularly those with lower dimensionality,
Why is that?
because its search time is essentially constant, regardless of the total size of the index. But generally, the accuracy and recall are lower compared to the graph-based HNSW or the clustering-based IVF methods.
So understanding these different indexing methods is crucial.
It is, because they represent the engineering compromises that turn this abstract concept of meaning detection into a real-world, millisecond-fast operation.
That mechanics section really establishes the foundation.
Hmm.
Now, I want to pivot to the revolutionary impact this technology has on methodology, specifically for researchers in the humanities and social sciences. This starts with the rise of what's called computational social science, or CSS.
CSS is this rapidly evolving academic field that uses computer science methods to analyze vast quantities of digital data. I mean, everything from social media posts and news archives to millions of digitized historical texts and government speeches.
And this marks a profound methodological shift in how that kind of research is done.
It's a whole new paradigm. Instead of the traditional qualitative research where an expert might interpret, say, 50 texts very deeply, you are now viewing text as data.
Which lets you track macroscopic societal patterns.
And microscopic changes in meaning across literally millions of documents at the same time.
And vector databases are the essential enabling engine for this. Historically, quantitative text analysis relied on, well, pretty simple frequency counts or dictionary-based methods.
Yeah.
What's called the bag of words model.
Which is a terrible name.
It is. And it treated text like a collection of isolated tokens.
So it lost all context. If the word tax appeared, it had no idea if it was used in a context of tax avoidance, which is negative, or tax relief, which is positive.
Exactly. The new paradigm, which is powered by word embeddings and vector DBs, is rooted in this 1957 linguistic insight from John Firth. A word is known by the company it keeps.
And the embedded model maps words based on that context, capturing the contextual meaning.
This is really where the vector DB infrastructure democratizes research tools. Before this infrastructure existed, a researcher had to painstakingly train their own specialized word embedding models, like Word2Vec, on their specific historical corpora.
Which is a complex, resource-intensive, and highly specialized programming task that most historians or sociologists just don't have the skills for.
Right. But now, they can leverage the massive storage and indexing capacity of a vector DB. They can take billions of documents, pre-vectorize them using powerful generalized models, and just store them.
A researcher in history or sociology can now skip the complex model training entirely and apply these sophisticated semantic queries immediately to their vast archives.
It shifts the barrier of entry from machine learning expertise to domain expertise. You just need to know your field and what questions to ask. So let's look at the academic significance. Specifically, through three critical dimensions of semantic analysis, our sources highlight. The first one is highly relevant to social studies, measuring hidden societal bias and stereotypes.
This is a really ethically important and methodologically rigorous application. Since these text corpora, all the books and articles we've ever written, reflect actual societal perceptions, the vectors capture those underlying biases.
So we can quantitatively measure how prejudices, gender, race, professional roles are embedded in our collective language.
And the power here is that it provides objective, data-driven proof. You can mathematically prove the existence and shape of a prejudice.
How does that work in practice?
Well, researchers can analyze the geometric vector relationship between, say, male noun plus doctor and female noun plus nurse. They can then demonstrate that this spatial relationship in the vector space is mathematically similar to the relationship between computer programmer and homemaker.
So it provides quantitative evidence of these professional stereotypes in a way that just reading and interpreting could never achieve.
It shows how the text itself, through learned word relationships, perpetuates these social biases. It turns an abstract societal concept into a measurable geometric phenomenon. It's a truly chilling moment when you realize that societal prejudice isn't just an idea, it's literally quantifiable as a geometric distance in an algorithm.
That is powerful. Okay, moving on to the second dimension, conceptual history research. This is about tracking the semantic shift of key political or social concepts over time.
Right, concepts like liberty, nation, or democracy are not static. Their meaning shifts based on their surrounding context in different eras.
So a researcher could partition a massive digitized archive into decades, newspapers from the 1950s, the 1960s, the 2020s, and so on.
And then they train an embedding model specifically on each of those time slices of text.
So the democracy vector learned from the 1950s newspapers will literally point in a different direction in the vector space than the vector learned from the 2020s papers.
Exactly. And the critical step is then analyzing the nearest neighbors for that concept in each of those historical databases. For example, if you query the archive trained on 1960s texts for the nearest concepts to democracy, the results might be something like anti-communism, Cold War alliance, or freedom.
But if you query the 2020s archive, the nearest neighbors might shift completely to citizen participation, fairness, diversity, or inequality.
And that shift quantitatively demonstrates the changing semantic profile of the concept. The process moves conceptual history from a purely qualitative interpretation, a historian reading and inferring, to quantitative proof that the meaning of a key political signifier has objectively evolved.
And there are real projects doing this.
Yes, projects like Stanford's HistWords, which analyze millions of historical texts, rely fundamentally on this vector analysis technique.
Okay, finally, the third dimension, discourse analysis and framing. This helps researchers map these vast, complex public discussions.
Imagine vectorizing hundreds of thousands of documents about a major social issue, like climate change policy or immigration. By applying clustering algorithms to these document vectors, a researcher can visually discover distinct frames or hidden discourses that weren't immediately visible by just reading through them.
Oh, so this is how researchers can actually map polarization.
Precisely. For instance, a study of news articles and online commentary on immigration might vectorize, say, 50,000 mainstream news items and 500,000 forum comments. The vector space visualization using tools like UMAP will show clear, isolated clusters,
The news articles might group tightly around frames like economic labor and multicultural policy.
while the online commentary forms a separate, very clear cluster around concepts like social conflict, security threat, and crime rate.
That clear semantic separation measures the semantic distance between those two discourse groups.
It visually and quantitatively maps the entire discourse landscape, demonstrating the existence of online echo chambers and polarization. And critically, it overcomes the inherent bias and limitations of using small, qualitative samples, which is how traditional discourse analysis had to be done.
And crucially, this doesn't stop at text. The revolution extends to what's called digital humanities, by handling non-text data thanks to multimodal embeddings.
That's right. Vectorization works on images, audio, and video just as effectively as it works on words. Historians can now vectorize massive archives of photos, dividing them into grids and analyzing the visual features.
So they can track the visual changes of a cityscape over 100 years.
Or measure the severity of poverty by tracking changes in building materials or street cleanliness from photos. This opens up entirely new avenues for research into cultures that have limited textual record.
And for other fields.
Musicologists can analyze the emotional similarity of audio clips to study genre influence, quantifying how one musical theme influenced another purely through the vector representation of the sound profile. It's a whole new world of data.
The connection between that academic realm and the professional world is this massive scale of unstructured data.
It's the same problem.
The same technology that analyzes millions of historical speeches can be leveraged to analyze a small law firm's millions of internal precedents, or as solo consultants' years of proprietary market research. We move now to the immediate practical value for specialized professionals.
And these scenarios show how vector DBs move from a theoretical concept to something that generates hard ROI by maximizing the value of the data assets people already have.
Let's start with small law firms. They need high-speed, accurate precedent discovery and rigorous contract review. Their biggest challenge is dealing with client input and finding relevant case law that isn't indexed by precise keywords.
That's the natural language case search problem. Traditional systems are rigid. They require exact legal terms. A lawyer's client, however, describes their situation in plain, messy, natural language.
So the vector search solution allows the lawyer to input the client's complex natural language query directly. For example, a case where a tenant can claim damages for mold due to a landlord refusing to repair ceiling leaks, and the lease was ambiguous on who was responsible for maintenance.
It's a complex situation, and the system immediately vectorizes that entire situation. It then finds the 10 or 20 most semantically similar precedents in the firm's own database, or a major legal database.
Even if the original case was filed under different legal code sections or used synonyms for mold or leak.
Right. This dramatically increases the discovery probability of those crucial hidden relevant cases that a normal keyword search would have completely missed.
And the power of RG integration here is essential, I would imagine.
Oh, absolutely. The RI system doesn't just return a list of case numbers. It retrieves the most relevant semantic sections of those cases and generates a concise summary, often less than a page, of the key issues, the applicable statutes, and the rulings instantly.
So it cuts down research time from hours to minutes.
Literally.
The second challenge for them is AI contract review, specifically identifying poison clauses in non-standard contracts, which are a huge time sink.
And very high risk. Manually reviewing a 50-page M&A contract, especially against standard templates, is prone to human error and takes hours and hours.
So the vector solution preloads a dedicated vector DB with standard clauses and a whole library of unilaterally unfavorable or risky clause vectors.
Then, as the AI contract review solution uploads new contract, it vectorizes each clause, the indemnity clause, the force majeure clause, the termination clause, and compares them to what's in the database.
So if the new contract's indemnity clause vector is semantically too close to a known risky vector in the database,
The system immediately flags it as a potential poison clause. It might even alert the lawyer. This clause is 95% semantically similar to clauses found in past disputes where the client lost major liability protection.
and it can also ensure comprehensive coverage. It can detect if a necessary standard clause, like a complete termination clause, is just missing entirely.
Yes, because the expected conceptual slot remains unfilled in the document's vector map. It minimizes legal risk and maximizes efficiency in a huge way.
Next up, small or solo consultants.
For individual or small team consultants, their knowledge base is their primary asset. They face the twin challenges of synthesizing massive amounts of external market data and managing their own fragmented internal knowledge.
The first challenge is market analysis and trend reporting. Consultants need to analyze hundreds of competitor reports, news releases, and industry studies to generate deep insights for their clients.
And traditional analysis only tells them, for example, that the word innovation appeared 300 times last quarter. That's a very shallow insight.
It doesn't tell you how it was used.
Not at all. Vector search allows for deep contextual trend analysis. A consultant can query their entire database of competitor documents. When competitor A uses the word innovation, was it used in a context semantically closer to product feature overhaul or to organizational cultural change?
And because the model understands the surrounding context, the consultant gets a nuanced answer, like 85% of their usage of innovation is in close semantic proximity to product roadmap execution, suggesting a tactical rather than strategic focus.
Exactly. Or they can query the relationship between concepts, which is far more powerful. Find key insights where sustainability and cost reduction were semantically close in market reports over the last 6 months.
This generates sophisticated reports based on the relationship between concepts, not just word frequency, delivering higher value insights instantly.
The second challenge is their own internal knowledge management, their own fragmented assets. Successful proposals, client summaries, old emails, notes from internal meetings. It's a mess.
This is the perfect RAG application for protecting that intellectual property and boosting efficiency. The consultant stores all their past work, potentially a decade of complex documents, in a personal, proprietary vector DB.
And then they can query their AG chatbot. Summarize the expected benefit slide, the main client objections, and the successful counterarguments from our most successful past projects related to logistics system efficiency for a new retail client.
The RAG system retrieves and synthesizes the logic and the content from the most relevant past projects, and crucially, it cites the original source file and even the page number where the information was found.
It maximizes proposal efficiency by instantly generating content that is grounded in proven past success. It's like having a perfect memory of everything you've ever done.
Let's move to authors and writers.
For authors, journalists, or historical novelists who are dealing with these deep qualitative archives, thousands of pages of primary sources, interviews, diaries, the sheer volume makes traditional research practically impossible.
So, challenge 1. Archival research. If a historical novelist is dealing with 500 transcribed interviews with, say, wartime veterans or independence activists, reading them all is impossible. but they need to find specific, emotional, conceptual moments.
So the author can query their database of transcribed sources with natural language, searching for concepts or emotions, something like, find all testimonies describing the moment they witnessed a comrade's death but nonetheless held on to the abstract concept of future or hope.
And the system uses semantic similarity to find contexts and anecdotes semantically related to hope passages describing imagining a liberated homeland, or planting a seed for my grandchildren, or writing a final letter to my son.
Even if the exact keyword hope was never mentioned in the transcript, this elevates the richness and authenticity of the writing by locating profound emotional resonance that would be impossible to find otherwise.
Challenge 2 addresses creative inspiration and writer's block, specifically escaping cliché when describing abstract feelings like solitude or existential dread.
We've all been there.
Absolutely. So the author can build a personal inspiration DB of, say, 1,000 deep, complex texts they admire, philosophy, novels, poetry. Then they input a draft paragraph they've written about solitude as a query into their own semantic search engine.
And the system returns passages with a semantically similar emotion or theme or stylistic approach from works like Camus the Stranger or Rilke's poetry. The author is given adjacent creative influences. It moves from subjective browsing of books to objective proximity in the semantic space, expanding their idea beyond their own linguistic habits.
Finally, let's talk about YouTubers and content creators.
For them, vector search tackles the problems of just massive media volume and overwhelming audience feedback. Time spent editing or analyzing comments is time lost creating.
Challenge 1, B-roll video management. Professional YouTubers often accumulate 10 terabytes or more of footage with generic file names.
It's a nightmare. Searching for the right feel or aesthetic is agonizing when you can only use file names or manual tags.
So, using multimodal search, an AI tool can vectorize the visual and auditory information of the video clips. The search goes beyond keywords like sunset or car.
So creators can search using abstract, emotional keywords, find all clips with an energetic morning city feel, or quiet and lonely Dawn Street.
How does that work for video?
The multimodal embedding model analyzes things like color saturation, motion vectors in the frames, and audio frequencies to quantify the clip's atmosphere. The AI instantly presents 10 clips based on that visual meaning, which drastically shortens the editing time.
That's a huge efficiency gain that directly translates to more content output.
Absolutely. Then challenge 2. Viewer feedback analysis. Thousands of comments on a popular video are too many to read, meaning crucial, actionable feedback often gets missed.
So by using semantic clustering tools, all 5,000 comments are vectorized and automatically clustered based on their meaning. The YouTuber gets an instant, high-level dashboard.
It shows the overall emotional sentiment and the largest topic clusters.
For instance, the dashboard might show, praise for product A is the largest cluster at 30%, the intro is too long is 15%, and question about the background music is 10%.
And this delivers immediate, actionable insight. You know exactly what to fix in the next video or what content resonated without manually wading through every single comment. It's transformative for creators.
As powerful as this technology is today, the ecosystem is evolving at, well, lightning speed. We see 3 major trends focused on pushing the boundaries of accuracy, utility, and crucially, scale.
Right. And trend 1 focuses on merging the best of the old and the new. Hybrid search. We established that vector search excels at meaning, but it can be poor for the specific precision required for things like product serial numbers or proper nouns.
Which are the strength of traditional lexical search.
That's right. So hybrid search is the intelligent merger. 2 engines run concurrently, the vector engine for semantic meaning and the lexical engine for keyword precision. The goal is to maximize relevance by satisfying both criteria.
But how does the system combine the results? If one engine ranks a document highly and the other ranks it poorly, how do they decide the final result order?
They use a complex algorithm designed for this exact purpose. Reciprocal rank fusion, or RRF. RRF takes the rank list from the lexical engine and the ranks list from the vector engine and merges them, assigning a unified score.
Okay, give me an example.
Imagine the keyword engine ranks document A as number 1 because it has the exact part number you searched for. But the vector engine ranks document A as number 100 because it's conceptually irrelevant to your overall intent.
So RF has to find a weighted compromise.
Precisely. RF uses a sophisticated formula to mathematically find that compromise, perhaps ranking it number 10 overall. It ensures that results are both contextually relevant and satisfy the precision requirement. This fusion approach represents real technological maturity. The new tech integrates with the old rather than just replacing it and delivers a much more robust user experience.
Trend 2 is the undeniable market driver. Its role as the brain of generative AI, especially ARGI, or Retrieval-Augmented Generation. This is the mechanism that takes LLMs from parlor tricks to reliable, professional tools.
It really is. We know LLMs fundamentally suffer from three critical weaknesses. They lack current or up-to-date information. They are ignorant of private or proprietary internal data specific to a company or a user. And they suffer from hallucination.
Making up facts.
Right, making up facts because they rely on probability, not verification.
And the VectorDB is the architectural solution to all three of those problems. It acts as the LLM's external fact-checked memory.
That's it. When you ask a question in an RG system, the query doesn't go straight to the probabilistic LLM. It goes to your VectorDB first.
Which is loaded with your company's latest documentation, compliance records, or proprietary research.
The VectorDB retrieves the most relevant, context-specific documents, the verifiable facts, and those facts are then augmented into the prompt that gets sent to the LLM.
This forces the LLM to generate an answer that is grounded in the provided facts.
Which drastically reduces hallucination and ensures accuracy based on the latest context that you control. VectorDBs act as the LLM's external plug-and-play memory, which can be quickly and cheaply updated with new information, effectively scaling the LLM's knowledge capacity infinitely and cheaply.
Trend 3 deals with the massive scaling challenges we touched on earlier. The fact that high-performing ANN algorithms like HNSW require the entire index structure to reside in high-cost RAM.
The financial bottlenecks.
For handling billions of vectors, it's prohibitively expensive at a global scale.
It is, and this necessity has driven intensive research into what are called disk-based ANN solutions, specifically to cut server costs while maintaining performance. The most notable effort in this space is from Microsoft, and it's called DiskScan.
So if we're moving the index structures from volatile high-speed RAM to slower, persistent SSDs to the disk, how big is the performance hit, realistically? Are we just moving the bottleneck from RAM cost to search latency?
That is the central engineering challenge. DiskScan attempts to optimize this trade-off radically. It aims to store the bulk of the less frequently accessed vectors and index structures on cheaper SSDs. But critically, it uses sophisticated page-level caching and optimization strategies to ensure that only the absolute minimum data needed for the active search path is loaded into RAM at any given time.
So the goal isn't to be as fast as pure HNSW and RAM.
No, but to be fast enough, say, within 10 to 20 milliseconds at a fraction of the cost. It's a massive efficiency play, and it's what will make the technology globally accessible at scale.
And related to scaling is the challenge of dynamic data management. If you're running a live service, your vector index has to support continuous insertion, deletion, and updating of vectors.
Which is difficult for these static graph-based indexes. If you add a billion new documents, you can't just rebuild the entire graph every hour.
So what's the solution?
Newer research, like a system called LSMVEC, is integrating the graph index structure with something called the log-structured merge tree, or LSM tree. That's a system common in traditional databases for handling high-volume write operations.
So it's another hybrid approach.
It is. This hybrid structure supports both high-performance search and the frequent dynamic data changes that are crucial for real-time services.
And the market clearly sees this infrastructure as essential. Our sources are predicting explosive growth for the VectorDB market, a compounded annual growth rate potentially hitting over 20%, leading to a market value well into the tens of billions of dollars by the early 2030s.
And the market dynamics confirm this. We see specialized startups like Milvis and Pinecone pushing innovation, but critically, we also see the established database giants like Oracle, AWS, and Elastic integrating vector search as an essential native add-on feature.
It's not a niche product anymore.
No. Oracle, for instance, has baked AI vector search directly into its core database. This integration confirms that vector capability is moving from a novel, specialized tool to a fundamental, expected database capability.
As we synthesize everything we've covered, the narrative of vector search is, I think, very clear. We are watching the definitive transition from the keyword era, where machines required rigid, precise input, to the context era,
where machines finally understand and can navigate human intent and conceptual meaning.
This is the definitive end of the semantic gap.
And this technology is such a potent force because it acts as a convergent solution across so many different sectors. It serves as that verified long-term memory for generative AI, grounding those models in fact and cutting down hallucination.
For the academic world, it is not merely a tool, it's a new methodology. It's enabling quantitative analysis of complex, nuanced textual meaning that was previously restricted solely to subjective, qualitative interpretation.
And for the professionals we discussed today, the lawyers, consultants, authors, and creators, it is truly a compass for exploration. It helps them seek and extract maximum contextual value from their own non-structured data assets. It turns their internal archives and chaotic data streams into organized, context-aware knowledge pools.
It is a complete revolution in knowledge access and professional efficiency.
And the future promises a world where virtually all data, text, image, audio, even 3D and IoT sensor data will be stored in a single, unified semantic space. As the fundamental interface for interacting with data shifts from simple, brittle keywords to complex, flowing meaning, this raises a crucial practical question for you, the professional or researcher.
And what's that question?
How will you redesign your own professional knowledge infrastructure, your personal archives, your company's data flows, to maximize your ability to explore the closest meaning in this growing data tsunami?
A profound and necessary question to consider as this technology rapidly becomes not optional, but essential. Thank you for joining us on this deep dive into the world of vector databases and the successful search for meaning.
We encourage you to continue exploring this powerful new technology.